All right, let's jump right in. Today, we're going to follow the entire journey of an idea, from the moment it pops into your head to the second your computer actually does something. We are going to pull back the curtain and demystify what really happens under the hood.
I mean, seriously, have you ever stopped to think about it? It seems so simple, right? You type 5 plus 7, hit enter, and poof, 12 appears. But what actually goes on in that tiny fraction of a second? That's the mystery we're going to solve today. We're going to follow that simple command from the very beginning all the way to the final answer. So, here's the thing. Before a computer can do anything at all, it needs a plan. And I don't just mean any old plan. It needs a perfect, step-by-step, absolutely foolproof set of instructions. There's zero room for error. And in the world of computing, we've got a special name for that kind of plan. Okay, I know, that sounds super technical, but let's just focus on two keywords: explicit and unambiguous. All this really means is that every single step has to be crystal clear. There's no kinda or maybe. It's just a super precise recipe for solving one very specific problem. And this right here is a perfect example. It's a simple algorithm for adding two numbers. You can see it starts, it declares its variables, it reads the values. Every single tiny step is laid out in a clear, logical order. This is basically the blueprint, written in a way that we humans can easily understand.
Now, if you want to make that logic even clearer, you can use a flowchart. It's just a visual version of our algorithm. Those ovals show you where it starts and stops. The rectangles, those are the actions, and the diamonds are for making decisions. It's literally a roadmap for how our program is going to think.
So we've got our flawless plan. Awesome. But how do we actually tell the computer about it? I mean, a flowchart is great for us, but the machine itself needs something much more structured. We have to translate our algorithm into what's called a programming language. And right here, you can see that translation in action. Over on the left, you've got the steps from our algorithm, and on the right, that's the basic skeleton of a program written in a language called C. You can see how our logical steps, like declare variables and add numbers, are going to become the actual code that fills in the body of this program. This is how we turn a simple plan into real code. Now, I've said the word variables a few times, so what are they? Honestly, the easiest way to think about them is just as labeled boxes. When our algorithm says declare variables num1, num2, and sum, we're basically telling the computer, hey, I need you to set aside 3 empty boxes for me. I'm going to call them num1, num2, and sum, and I'll be putting some numbers in them later. This image is just the perfect way to visualize it. Variables are like those open boxes. You can change what's inside them whenever you want as the program runs. But constants, those are like sealed boxes. Once you put a value in there, like the number pi, for example, it's locked in. You can't change it. Okay, so let's recap. We've gone from an idea to an algorithm to an actual C program. It feels like we should be ready to go, right? Well, not quite. There's one more crucial final translation step, and this gets to the very heart of how a computer actually thinks. Because the big secret is that the C program we just wrote is complete gibberish to the computer. It doesn't understand the word int or main, none of it. Because at their most fundamental level, computers only speak one language, binary. And why is that? Well, a modern computer chip has billions of microscopic little switches called transistors. And a switch can only be in one of two states, on or off. We represent on with a 1 and off with a 0. And that's it. Every single piece of information, every number, every letter, every instruction is just a long sequence of these ones and zeros. Check this out. Here's that translation in action. The number 216, to us, becomes 1101000 in binary for the computer. Each spot in that binary number represents a power of 2. And by just adding up the values where there's a 1, the computer can perfectly reconstruct the number 216.
And don't think this simple system is just for positive numbers. Oh no. Using a really clever method called 2's complement, which you can see here, computers can also represent negative numbers perfectly fine. It's an incredibly elegant system, built entirely on just 2 states, on and off. All right, we are in the home stretch. We have our human idea, and it's been translated all the way down into the computer's native language of ones and zeros. So now it's finally time to see how the physical machine, the hardware, actually gets the job done. So this diagram shows the final steps. First, our C program gets fed into something called a compiler, which translates it into a lower-level language. Then an assembler takes that and turns it into object code, which is almost pure binary. And finally, a linker grabs that code, bundles it with any other bits and pieces it needs, and creates one single executable file. That file, that is the final product. It's pure binary instructions the processor can finally understand. And this is where the magic happens. That executable file gets loaded into the computer's memory. The CPU, the central processing unit, the brain of the whole operation, fetches our instructions, that series of ones and zeros that means add these two numbers. A special part inside the CPU, called the arithmetic logic unit, does the actual math, and the result is sent off to be displayed. Finally, after all that, we see 12 pop up on our screen.
You know, after seeing this whole journey, it really makes you think, doesn't it? We started with a simple human plan, and we ended with a machine flipping billions of switches every single second. The computer isn't some kind of genius. It's not thinking. It's just executing. It's an unbelievably fast and incredibly obedient servant, just following our perfectly laid out instructions to the absolute letter. And that is what really happens when you just add two numbers.